Yo, what's up, everybody? Welcome back. Today we are working on our B tree implementation in Zig, and today's task is trying to fix insertion again. This is our B tree. This is current state. What we are seeing is a root node here. He's got the number 28. 28, boom, goes in the root node. Wow, huge. 76, boom, also in the root node. 92, also there. 23, also there. Now, how a B tree works is when the root node fills up, he can store some number of elements. This is like a configurable number. But when he fills up, he basically needs to split this node in some way. So what's going to happen here is he's going to try to put the 68 in sorted order. He's going to go like, whoop, 68, boom. And what's going to happen is he's going to go, uh-oh, we gotta split these things. What's the best way to split them? Well, I guess we'll split them by the middle element. So 76 and 92, boom, new node, 68 over here, right? So that's what we're gonna see here. He's gonna go, boom, split these guys based off the 68. 68 goes in the root. And so the B tree iteration order is like, you kind of just walk down the left side of the tree, 23, 28, and then you go, oh, okay, let's look at his parent, 68, then go to his right, look at those guys. So we get some more guys, they try to fill in the leaves, boom, boom. We get a 27 in here, same problem. He's like, uh-oh, too much room. So this guy comes down here. He goes, oh shit, too much stuff. 28, pop them out. And then the 34, 35 come into their own node. 28 tries to go into the parent. So that's what we're gonna see here is 23, 27, 34, 35, they get their own nodes. 28, boom, into the root. Chill. Everyone's happy. This goes on for a while, right? Until we get to the point where we can't, oh fuck. Hold on. I clicked too many times. Until we get to the point where stuff does not fit in the child node anymore, right? So this guy, it's this one. The 79 comes down here and he goes, uh-oh, too much stuff. 86 pops out. 91, 92 go down below. 81, 79 here. Now the problem here is that this guy only has 4 split points, which means he can only have 5 children nodes, right? Because like we were saying, the iteration order has to be the stuff on the left of this, then the stuff on the left of this, and the stuff on the left of this, and the stuff on the right of the end thing, right? So what's going to happen here is 86 comes up here, and we go, I guess we have to split this root node. 68 comes out, and what's going to happen here is like these 23, 28 are going to become like their new children of the root. So I think that is shown here. Boom. Yeah, so we get here, like, the whole tree was split in half. Like this. 23, 28 are left of 68. 76, 86 are on the right of that. And they bring, like, all of their children with them. Super chill. We run for a little bit longer, and our thing starts to fall over here. And I think I can show why. So this 42 comes down here. Boom, boom. He goes, uh-oh, split new node here. Boom. And what we should do is somehow find a way to like leverage this empty space down here, right? The root node still has plenty of extra room. But we don't do that. What we do instead is we go, well, if we're full, we must have to go another layer down, right? Because that's what we did on the first layer. We go another layer down. We go, oh, let's take the 1023, put him here. The 2836, put him down here. Boom. This is it. We're perfect. The 42, he goes up here, just like we did before. And this is like a valid tree in terms of like, if you were to iterate this thing, I think it's like correct. Right? You have 2, 6, 7, 9, 10, 13, 19, 23, 24, 26, 27, 42. Then you go to the right of the 40. Oh, no, this is just like totally fucked. Never mind. I was going to say maybe this would be right. It's not right because the 42 does not bisect the 2836. So we've done something totally stupid. What probably should have happened is that we should have found some way to like leverage the siblings. So let's just spam this click button a few times until we get back to that state. Maybe we should, automatically end up there, but you're not my boss. You can't make me. I think it's here. Okay, so what should happen is the 42 comes down here. He goes, uh-oh, too big. 42 comes up a layer. The 46 and 50 get their own node. Boom. And we have to figure out now what happens here. I guess the 28 comes out, right? Because he's in the center of this. And now somehow this like 3642 needs to like go somewhere. This 1023 probably means that like these nodes need to get split up. somehow, right? So like 2, 6, 7, 9, less than 10, that's sane. 13, 19, less than 23, that's sane. 24, 26, 27, greater than 23, that makes sense. So I guess probably like this stuff comes over here as well with this guy, right? Boom, boom. Um, and now I guess what we have to do is we have to figure out where this stuff goes, right? So like we can tell looking at this that this stuff is like smaller than this stuff. So he probably goes like in between here, right? So we go, the 28 goes in here. He goes, oh, I'm less than 68. Boom, we've got room here. That's chill. So then now we know that like the stuff that we brought up here with the 28 goes here. That's kind of like what I'm thinking. I will say that there's probably like a correct answer to how this insertion is supposed to work. But we don't like cheating around here, and looking at the answer key is cheating, right? So we're experimenting with ideas until we get something that's like kind of correct, and then we'll figure out how reasonable it is. Okay, so we've kind of like figured out that what we want to kind of like bring like a tree up the stack with us as we kind of iterate up to the root. Eventually, we'll get to the root and we'll say, oh, we'll find someone on the way up that has space for us, right? And once we find that space, we insert this whole subtree, just kind of like boom, right into that spot. And so we need some way to like represent this. Now, node storage. The way our node storage works is we say the first node, 0, is the root. Then let's say that we have 2 children per node. 1, 2. So this is the first child 0, second child 0. Cool. Boom. Then we go 3, 4. 3 is the left of 1, 4 is the right of 1. 5, 6. 5 is the left of 2, 6 is the right of 2. Boom. So we kind of like store like layers of stuff, and we were hoping that we could kind of implicitly store the relationships between nodes based off where they're stored here. I believe this storage makes it really hard to do this. Really hard, right? Because like, where does this like 34, 35, 39, 41, 46, 50, 36, 42 go? We don't know where they belong yet. And so like, as we walk up the tree, they have to go somewhere, right? And so I guess we could store them in like an intermediate place and then copy the whole subtree, like resolve the whole subtree later, right? So we could go, okay, so we know that this has to go here. So we'll take all of this data and copy it into the right spot. So this 72, 70, 72, 75, this has to like go, well, this is like the third layer. So that means that we're looking at indices like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 11, 12, and 13 need to move 5 forward, and then this stuff can suit in, and then 76, 86 need to move 1 forward, and then we have room to slot this stuff in. But that's like a pain in the ass, and I suspect slow. I was kind of hoping that by doing it this way, we could avoid like having node pointers everywhere, but now I'm kind of leaning towards maybe that's the right way. Somebody on stream, when they were watching, they were like, you're going to regret this later. And I was like, what do you know? Nah. But I think we're at the point now. I regret it. And so the first task, I think, is updating our storage format. Fuck this shit. I think that I'm going to just say we have nodes in here that have indices, right? And I think we can still keep it so that 0 is the root node. Cool. But I think that what we'll do is every time we are going to have our root node say, nodes 1 and 2 are going to be my children. And then node 1 is going to say 3 and 4 are my children. And then as we kind of like construct this tree, we can kind of like put this node in here, right? So like this node would just be like node 6. And node 6 would say, well, this stuff used to have nodes like 3, 4, 5, 6 as his children. So these guys were like here before, right? 34, 35. These guys were in here. 30, 39, 41. These guys were in here, right? So as these come out, now all we have to do is like say, okay, our new node 6 has, 3 and 4 as his first 2 children, and then like 7 as his third child, because like we added a new node to this thing. So we'll allow for like kind of like non-contiguous node iteration. Our nodes should be hopefully big enough that like the cache improvements of these like B trees of having multiple elements in a row. I'm hoping that like if the nodes are big enough, then like the random kind of jumping by node ID will not be that expensive. I'm hoping, but I mean, maybe we can find some ways to improve that later. But at the very least, this will simplify our initial implementation a lot. So the first step is to fix our data storage format. Then we can like do this, like bring the nodes with us as we walk up the tree. Then we can fix our insertion. That's the fucking plan, baby. That's the plan. Let's fucking move. So. Here we have our storage. I guess our nodes have to store. Here he was storing elms. I guess this is keys now. And he should also store children. And his children are going to be node IDs. Yes. The wrong way though. He's going to have num children node IDs. Let's think about this for a second. So as we walk the tree, I'm wondering if storing these two guys like back to back, like in the same structure here, is kind of like bad for memory. But maybe we'll just do it this way for now and split them out later if we need to. There's a possibility that like you might not need to look at the children every time. I'm not sure. Maybe this is fine. Maybe it's fine. This guy says, here are how many children I have. Cool. Or how many keys I have. So maybe we call this now num keys. I feel like that makes it clear. And then we'll just say num children is equal to num keys plus 1. And then we'll also note in here that that makes it sound like there's always a child. Which there is. Nodes, except for the root, cannot have less than capacity over 2 children. So now the question is, how do we represent the root? How do we represent the root? We can't. So maybe it's better for this to be num children, right? This guy's num children, which means that he can be 0, and then we'll say num keys is equal to num children minus saturating sub 1. Yeah, that seems reasonable. And we can actually encode that right here. We're using this thing child index. This is like a bad name, but fuck it. I guess usize is fine here, actually. Yeah. We'll return self dot num children saturating sub 1. If num children is 0, we are 0. In other cases, we are 1 less. Boom. Okay. Cool. We should also note that like shouldn't ever be possible to have a single child. Shouldn't ever be possible. Okay. So this is gonna break all sorts of shit. And I wonder if if it's better to just read the code top to bottom and try to fix it as we go, or follow compile errors. We can try following compile errors and see if that makes sense. No build step name check, that is fair. Okay. You know what? It's almost like this is like a new thing. I feel like it's easier to start from scratch here and work our way up. Just because like it's so different. So let's do that. Yeah. Let's do that. B tree 2, baby. Just because like it's like the common code between this and the existing implementation is like near none, because everything is about iterating the data and the data's changed. So B tree 2, baby. B tree 2, B tree 2, exe2, baby. All right. Zig builds here, I guess. And B tree 2. Hell yeah. Okay. Well, I guess we want the visualizer still, but I mean, it'll take us a while to get there. So maybe we just build this thing out to the point where we can run the visualizer again. That seems kind of reasonable. So we start like B tree. B tree 2 is going to have a very similar format to this guy. The existing B tree. Oopsies. Okay, so he's going to be like, I'm going to return some structure. My structure is going to have some sort of like storage of nodes. That's still true. That is still very much the case. Our nodes are going to have some format. Boom. Cool. I guess this is still going to look like this. Boom. And then can we like initialize this thing up front? Okay, here we go. Self is this, and we initialize. Boom. We need an allocator. Okay. We need some of these type defs. Sort elms. I believe that this guy is totally reasonable to copy out as well. And so when we append this thing, what happens? Okay. Okay, let's start here. Storage. So what did we say? We said this is going to be called keys, which is going to be node capacity. We said we were going to have children, which is going to be children of node ID. So we need to define this node ID, probably. Boom, boom. Probably we can get away with like, maybe we want to like shrink the size of this thing now. If not too much, can you briefly summarize the differences from the original B tree? Yes. That is a good question. So before, we had B tree implementation had implicit node IDs. So 0's children 1, 2, 1's children 3, 4, 2's children 5, 6, 3's children 7, 8, 4's 9, 10, right? We're kind of like implicitly storing this way. This, no bueno. Because we want to be able to like shuffle nodes around in the tree really easily. And we want to like kind of construct a node like a tree of like a hierarchy as we're kind of like walking up the tree and we don't know where it's going to go. So now basically we just need each of these nodes to store pointers to each of his children, right? So we're basically taking the node and converting him from this, where he has elements and number of elements, which are basically the keys. We're basically converting that to keys, children, and then what do we say? It was num children here. That's what we said. And then we said that here we get num keys by doing it was self num children saturating sub num. Yep. Yeah. Okay, so that's kind of like the only difference, and then it just turns out that that's probably going to result in a lot of changes everywhere. Like the whole thing is going to look different as a result of this. Okay, so I guess let's start by trying to make the root node. By pointer to children, you mean index to children. Yeah, same thing. But yeah. I guess not the same thing, but I mean them as the same thing. Okay, so let's start at the beginning. We will try to I guess, does there always have to be a root? Probably, right? So that's kind of what this guy's trying to do. He's trying to make a root initially, which I think is fair. So I think this does good for us. So can we just completely start this thing with the visualizer intact? That'd be kind of cool. So we can kind of build up our visualizer stuff with this as we go. So I guess that means that we're probably going to want to copy a lot of our like HTML shit. Kind of copy out our whole server. But we're going to start by not putting anything in the B tree, I guess. Or maybe we will allow ourselves to insert like 4 nodes, like up to, let's just try to fill the root up. We'll just try to fill the root up. I think that's a good start. So we create our insert sequence. We say test start is 4. And then here we're going to have to, I guess, just start by, for now, since we don't have any, I guess, what do I want to do here? I guess we probably want to start immediately with our insertion state machine. I think that makes sense. So here we had like inserter returns an inserter. And our inserter here went kind of crazy. We'll see if this guy kind of needs to be similar to how he was before. So he before was like, I have some value. I'm trying to insert that value into some place. And here is my current state. And yeah, that seems pretty chill so far. I think the implementation of this stuff is all going to change significantly. So I think what we do right now is we start at the beginning. We just start with an append and finish. No split. Fuck split. Fuck split. Append and finish. That's simple. We delete anything that looks complex here because he's not needed yet. Boom. And our inserter will just say, hey, I'm trying to insert this thing, baby. So we return, we're trying to insert some value. So val equals val, target is equal to, right now, we only ever can inject into the root node, and B tree is self. Okay. We need a root node definition. So this is kind of hard coded to node ID 0. Okay, chill. Why are you starting over again? Because the data format is just like so different that I think it's easier to do it this way. We're basically saying like, I want to change the data to have links to children directly in the node instead of being implicitly figured out based off of its position in the node array. I want to say like, you can move the nodes around without moving their positions in storage. And that's just like so different that it's worth running from the start again. Okay. So then we just need our like insert, which goes like, we're gonna insert this thing here, and this guy runs the inserter until completion. So he says like, give me an inserter. Give me an inserter. Actually, we probably don't even need this part right now. We don't even need that part yet. Okay, so in terms of visualizing, we need to serialize this thing in some way. So for now, we only need to return the root node and nothing else. We have our inserter to serialize, so that stuff kind of stays the same. It's more this like serialization of, I think it works. This actually is going to work the same way where we kind of return some sort of tree with some node storage. But we don't have like any like depth first iteration yet. We don't have our like depth walker yet. So let's just say that our tree is literally just going to return a single node. I think that they want an array here. I think I think he expects an object. And he's like, I have an object field that is node with the value of the root node. We only have a single root node right now. And then I think he also wants a children field here that is just empty. Yeah. So he wants like an array that's empty. That sounds right so far. And then so this tree object needs to be ended as well. Okay, cool. And then we send the node capacity, insert, we send the node capacity, the thing we're trying to insert, and the data, chill. Chill. Okay, so how much of this doesn't work? This thing has no D in it, true. So we will fix that. So this takes in ourselves, and he goes, storage D in it. Boom. Simple. All right, one problem out of the way. What's next? Key storage. This is just storage now. True. And then no field num elms here at 168. So this is when we're writing out the data. What is happening here? Oh, sure, that's fine. So this should be num keys. For each key, he's looking at the key here. Yes. Okay, that should be kind of good enough for now. Get by node ID. These functions were useful. Get by node ID and resize, as well as get by node ID. Those were sick. So these guys basically just converted from like the strong type of node ID into the index here. So we can just kind of copy these here. Key storage is now storage. HW question mark. I don't know what you're asking. So, okay, is this all the same? So here we're saying, yo, if this thing's too big, we need to resize it and then memset all the new elements to 0. Yeah, all this is the same. Cool. I mean, are you doing homework? No, I haven't been to school for like 10 years, dude. This is just fun. Okay. So this append doesn't exist anymore, which is true. And I guess we kind of want it to exist still. I think that's pretty reasonable. Okay. So in our new version of this thing, we're going to append some value to this thing. And in the new version of this, when we append a key, we need to create his children along with him. That is like the new constraint of this. So it almost feels like this can't be here anymore. Because unless we like pass in the B tree along with him, which feels kind of weird, this API just feels kind of wacky now. It's almost like append now is not a function of the node, but is a function of the B tree itself. Right? So we are saying like add to node is a better name for this now. And we're going to say the node that we're adding to is a node ID. Yeah, this feels more reasonable. This feels more reasonable. And so now what do? We get the node. And then what? This thing must probably use an allocator in some way, shape, or form. Probably the number of children that we add to this thing. I guess the first thing we do, yeah, it depends on the number of children we have now, right? So if node num children is equal to 0, then we need to make 2 new nodes, else it's 1. Right? So we can say like, I don't know how to do this. I guess it's kind of like completely different in these two cases. So here we make 2 new nodes. Self storage.append here twice. Okay, and then like A is like the length of this thing now. And B, we get like 2 values out of this thing. We append twice, we get 2 things. Cool. Then I guess then we have like node children. I guess it's like node children 0 is this. Node children 1 is this. Yeah. So we add our 2 children to the node. And then we need to like say that the keys 0 is a val. And then update num keys. Num children is equal to 2 now. Yeah. And this is like failure tolerant because these tries will like try to set these things, but in reality, like they won't be flagged as valid until down here. So I think we're chilling. Okay, so if the number of children is not 0, then we only need to add 1 thing. So this case is going to be like node. I guess we have to check here if node num children is equal to like this is a scary name. I guess can we call this like children capacity something? Just to make that a little bit more clear. Yeah, so if this is like, or this could be children len as well. That's a fair, we can do that as well. Children capacity, I kind of like that better. I like that better. So in this case, we return that we like can't. I guess an error. This might not be an error forever, but for now, this is fine. So can't fit. You know, out of memory or something. It's fine. And then the else case here is the happy path. So this is like the majority of cases where we're going to say node children at node num children is the current, you know, this guy. Then we append an empty node, boom. And then our keys at node num children -1 is val, I think. And num children plus equals 1, maybe? Does that make sense? So here you have, I guess we'll find out. When we visualize. Okay. So now this isn't called node append. This calls self btree add to node. Yes. And this is self target as the node ID and self val as value. Boom. And then we're finished. Wow. Look at us go. Look at us go. Okay. So that seems kind of reasonable now. 28 is mad because this should be a children capacity. Yeah, makes sense. Area unit is ignored at 71. Try. And then found usize 110. Oh, right. That's annoying. Next node ID, we'll call this. So this is like return a node ID with the value of self-storage items line. Boom. And then all of these guys are self next node ID. Boom. 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 All right. That should fix those. Node LMs at 298 is pissed off. There's just some print line. I don't give a fuck. Okay. 108. He's like, I expected a U32, found a U size. Yeah, okay. That's fine. So this thing runs. This thing builds at least. I wonder how it works. So we're hoping. Okay. So there we've got our root node working. Now he crashes because 68 tries to insert in here. We don't know how to split yet. So let's figure that out. So our old split did a lot of like manipulation of like indices using like these like node child like data getters and stuff, and then he had to like kind of like move data around and stuff. I think that we might be able to like get around that somehow. Split root probably still has to be separate, so let's kind of assume that for now. So we'll say, okay, here we probably want to check, we probably want to try this and return if it succeeded or not. I think that's kind of the same thing. So here we return false instead of out of memory. Now, when we call this, we say, like, it's weird to have a bool and an error at the same time, but it's like the bool is like an expected failure and the error is an unexpected failure. So, you know, it is what it is. Okay, so if we succeed, we go into the finish state. Else, we have to go into the append the split state. And how do we do this in our old version? So here we do the same thing. And then in the split state, we handled the root node specially. So I think that's pretty reasonable. So we just go like, okay, we split and then we append. That's what we want to do. Okay, sure. What the fuck is this thing called? Inserter. Okay. So, what does our split root look like? We probably have something very similar to the thing we did before, where we at least, the like sorting of nodes is all the same code. This like node splitter thing, this is great. So this guy gave us a way to like, he gave us a way to sort nodes, take the left half of them, take the right half of them, and take the center element, and kind of like easily propagate those to who they gotta go to. So I think that we will still use this guy. That seems reasonable. The rest of this is fine. So he does like, okay, we make an array that is like our node capacity +1 because you know we're out of room. So then we sort that guy, and then we just have like functions to get the left, right, and parent the center. Maybe this should be called center LM. I think that is more reasonable. Okay. So that means here we must have to like construct the node splitter. And we're like, we want to construct this with some node and the extra value. So the extra value is self val, and I guess the node is get by node ID self-target. That seems reasonable. So we kind of have this. Then, how does the split look for us? We need to, I don't know, do something. I'm thinking. So our node has keys and children. Does our node splitter have to keep track of the children as well? Kind of feels like he might. So as we split, what is going to happen? We're going to say, take the left two elements, the left, I guess, n elements, and the right n elements, and we're going to do something with them. We have to split them in half. So in this world, is like the 92 and the 93 come down here. The 28 and the 76 stay here. They stay in the node they were at before. No, in the case of the root, since we said the root node is always 0, they can't stay. But we could just change that constraint. We could just store the root node somewhere. Let's do that. So instead of the root node being hard-coded here, do we store it here? Like, that doesn't seem crazy. So then, in our case, what happens is we have, like, we have this stuff, which is not sorted, by the way. Feels like it should be. Feels like it should be sorted. So let's fix that. Node keys. So we have to be really careful here. Even this is fucking weird, because if we have children in this thing, they have to move along with the keys. But for now, we can just not think about that part. We'll just ignore that for now because we don't have children yet. We will come to that and we will find problems. But for now, let's not get ahead of ourselves. Okay. So this target now has to be self root node. Okay. And then 228, he needs to start with, I guess it's btree dot root node valued here. Okay, 165. Return true. We succeeded. Okay. And then 114 is pissed off because I don't know why we have this. Okay. So now that's not good. Where are those zeros coming from? That's really bad. Because this should be like node.keys from 0 to node num keys. True. And then also the node is this is sketchy because the node can be moved when the storage changes. So that's actually sketchy as fuck. This node pointer is gonna get invalidated by this move. So I guess we go like this instead. We just say like this, and then we probably double append here. It's probably resize here to the number of elements plus 1. or plus 2. Then we say that like old size was this. Yeah. Jesus. There's so many ways to go wrong here. Then here we memset self-storage items from old size onwards to empty. Now we can say node is self get by node ID, node ID. Now he's happy. No resizing that can be done here. This is sketchy, so this is going to be we can't do it this way anymore, which kind of sucks. So we have to do storage items len -1 here and -2 here. Okay, Jesus. Everything's so hard, man. Everything's so hard. Okay, so now here we go like new ID is this, we append, and then we say node children at node num children is equal to new ID, and then we get the node. So const node equals self get by node ID, node ID. We have to be very careful here. Very careful. Yeah, then in any case here, we reset. So we say const node is equal self get by node ID. This, and then we can sort. Okay. Woo, sketchy, 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 sketchy. True, this guy's pissed. We might have to increase this thing to a U size later, but for now, this is fine. Double pointer somewhere here. Boom, boom. All right. There, okay, so we have sorted values in here. Chilling. We take the 68. We try to put him in. He gets mad because nothing happens. He just gives the fuck up. So, now we have to handle that. It's the split time. So we take the left n elements. We take the left ones, we leave them. We take the right ones, we put them somewhere new. Seems reasonable so far. So I guess we say we need like new root is going to be like a new thing. Our new child is going to be another thing. Okay? So that's chill. I guess we have to do it the other way. So it's new root is self b tree storage. No. Next node ID. Yeah. New child like this. Boom. Okay. So we have a new root, new child. New child gets the 7692. So new child. This, I guess we're going to call these IDs. New root ID, new child ID. So I guess the new child ID. We need to set his children. So he's got a 76 and a 92 to put in him. And then theoretically, these like 76 and 92s, they have like children to go with them. So these are nodes. These are node IDs. No, these are values, but the values come with children, right? That's the part that we're missing here. So the keys we have in this world, we have 23, 28, 76, 92. And in these, the children are 23, 28. Like, we have children for 23 and 28, which are three to these children, and 3 of these children. That's what we're missing. So it means that when we pull the 76 and 92 out, okay, reset layout. Reset. He's not running. That's why. I need to look. I need to look. We need to look. Okay. Fuck. Num children equals children capacity, I guess. It's the better answer here. This guy is like, this guy's totally cooked. The node splitter has no fucking idea what he's doing. That's why we're looking at this. Okay. Boom, 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 boom. Okay, we take this guy. So these guys go to the right. This guy comes in here. Boom. This guy splits out. So, in the previous world, theoretically, we have these are attached to empty nodes, right? 23, 28 23 and 28 need to keep 3 nodes, and 76, 92 need to leave with 3. So how the fuck is that working? Right? That's the part that we're missing. So I think what happens here is that by 68 coming in here, he's kind of created like an implicit 6th node. Yes. So 76 and 92 need to come out here, and they need to bring the node that was created by the insertion of 68 plus their extra 2. Yeah, it's something like that. Something like that. So I think 3 new nodes need to be created here. And the node splitter, it needs to keep track of the child IDs as well. It's the only way. So I guess that means that like so depending on where this gets inserted, it must change how the things get allocated. It must. It must. It has to. Okay, I need to draw into the future for things that we don't have yet. So we have 1, 2, 3, 4 guys, and they have pointers to like some 1, 2, 3, 4, 5 children, right? So we take the 68, he comes in here, which means that like there's like a new guy here. Yeah. And then what happens is somebody gets ejected from this thing, and the right elms get sent to the right side, and the left elms here get sent to the left side. Yes. Okay. Okay, so we need to track that in the node splitter. It's the only way that makes sense. Which means that this... It means that we need to like create like a new... Yeah, we like... Split node. Split node. So this is common for everyone. Yes. So I guess he gets the node ID as well here. That seems reasonable to me. So we come in here, we're like, hey, here's a new value, and extra node gets this node ID. That makes sense to me. Extra key and extra node. So then what happens here? The node splitter, he needs... Does he need to allocate here? Probably, yeah, I guess, well, not allocate, but it feels like we want like left children is going to be like children capacity over 2. Like it feels like it should be something like split size node IDs. Yes. Right children should also be this. That feels kind of right. That feels kind of right. So now we need to like figure out who our left children are. So it's something like I almost want to go while I is less than extra key. And set I to be 0. And by I don't mean I. I mean I want to look at like, I want to look at these guys and I want to say, here's our extra key, 68. And I want to iterate these guys until I find where 68 belongs, which is here. So I want to go like for hit 23 and 28, right? So I go while the node keys at I is less than extra key. What do we do? we say with extra I don't know. We say like with extra at I is equal to node keys I. That's chill. But then we also want to say that like we need to figure out like the child array. Hold on. Maybe we do it like this. Yes. Okay, that makes sense. So we're gonna have like key index here and children index. And what we're gonna do is as we move forwards, we're going to insert into both here. And into the children. Yes. Now this is probably too much. This is extra tracking, but it's fine. It's fine. So what happens is eventually we hit this 68. Boom. And what do we say here? If we hit the 68, we do something. We say like ret with extra key index is equal to extra node or something. Right? And ret children at children index is equal to the extra node. It's extra node and extra key. Yes, that makes sense. So we go node 1, child 1, boom, new node, new child. And then we continue with the rest. So I think that we just have to make sure we got this stuff right. Yeah. So then we just go while key index is less than node capacity or something. We do like ret with extra key index is equal node keys key index. But this is offset by 1 now. And the children. Okay, there's like some extra tracking going on here. We need to do like ret children 0 is unconditionally. Yeah, that makes sense. Ret children 0 is unconditionally node children 0. Then here we can just use key index plus 1 everywhere. Yes. Then it's like this here. Okay, that sounds right. That sounds right. I'm not really I'm not 100% sure about that, but like maybe. So I think then surely this is going to be useful in some way, shape, or form. So we get our node splitter. And can we just look at like left children? Or can we just like print the whole thing? Can we even just like fucking, yeah, stood debug print. I'm really unconfident in this, but surely node splitter. Okay, we run it. We refresh. We put our shit in here. And now we should hit the node splitter here. Looks like he's just kind of infinite looping, which isn't good. Now, because here we're not deferring key index plus equals 1. So I'm a dumbass. We're just infinite looping. Okay, boom, 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 boom. Okay, so here we got a node splitter. We got nodes 23, 28, 68, 76, 92. So those are sorted great. We have our children here. We have the first 3 are 1, 2, and 4. So 4 is the new node. 5 and 0. This is kind of sketchy. I'm actually not sure now. 1, 2, 4. This should be full. I've done something wrong here. Can we look at like this? GDB. Let's B tree 2, GDB this bad boy. Refresh. Step. Oh, I forgot to hit the breakpoint. It's an important part of debugging is stopping at the code you want to look at. Okay. So how the fuck is extra node optimized out? What the fuck? Oh, okay, sure. So the new child ID is 6. So in this scenario, this X is a 6. Can we look at... I don't really know what I'm trying to see here. I think I guess I want to look at the node children here. So the node, the existing node has children 1, 2, 3, 4, 5. Great. So if we're expecting the thing to get split in the middle, that means we should see 1, 2, 3 on the left side and 6, 4, 5 on the right side, because 6 is the new node. Yes, 6 is the extra that's getting injected in here. And so our question becomes, are we in the right state here? So we've done the first half. We looked at 23, we've looked at 28, we've looked at 68. And our children have value of 1, 2, 3, 6, which is correct so far, right? That's what we said. We wanted 1, 2, 3, 6, 4, 5. So then is this right? 6, 0, 0. Okay. So 0, 1, 2, 3. So this key index feels like it's wrong. This should be +2. I was off by 2. The classic off by 2 error. The classic. Okay. So we put this shit in here, and we see now the correct order of stuff: 23, 28, 68, 76, 92. And then we have 1, 2, 3, 6, 4, 5. Boom. Okay, that's exactly what we wanted. Node splitter looking fucking good. So now all we have to do is like adjust our nodes to fix that. So our existing node, he's got to set children to okay, let's make it so that our node abstraction has a way to like set contents. Right? Simple, right? He takes in a node, he takes in the keys as a slice of T, and he takes in the children as a slice of node ID. Here he throws a quick assertion down that the children len is 1 greater than the keys len, right? Because that's the keys are supposed to split the children. And then we can just go like self num children equal children len mem copy from into self keys from 0 to keys len from keys. Okay, and we do the same thing with children. Boom, boom, boom. Chill. So now in here, we can just set the contents. We can say the existing node, he gets the left half of the split. Node set content. So he gets node splitter left. We should call this left keys now. And we should call this left children. And this is right keys, right children. I think that it's like this. I think it's like this. And this should be center key here. I just joined. Can you get an explanation of what you're making? Just 1 second. 1 second. This is left keys, left children. And let's just start there and see if the visualizer gives us anything sane here. He's pissed because left children is supposed to return node IDs here. That's true. True, true, true. Yeah, 1 sec, 1 sec. We'll get to the visualization and then I can show you. Num children here is pissed off because this has to be in cast. There we go. Boom. Refresh. Okay, so we are making a B tree. Our B tree is a little better than what you're seeing right here, but we're refactoring our data format to fit a new workflow. But the idea here is that you get an element, 28, boom, he comes in here. 76 goes in here. 92, boom. 23, boom. You have sorted elements in this node. Now the node is full. What happens when you get to 68? Well, in a B tree, what happens is the 68 gets like inserted in here in sorted order. And then we go, which element is the center? 68. Pull that out. And we say, okay, we'll split out 2 nodes now. A 76, 92, and a 23, 28. And what happens here, how this works is like the B tree goes, oh, 23, 28, those are less than 68. 76, 92, those are greater than 68. Boom. So you have this like tree of stuff where like children are kind of bisected by a split point above them. And we've been to Arctis for a couple days. We're kind of at the point now where we realized our data storage format was wrong. So we're kind of like building it back up from the bottom with a new internal format. Right children, no using with extra. I think it's probably, oh yeah. I mean, it'll resolve itself. So what we're hoping to see now with our current visualization is that we're hoping to see that when we insert this guy, we should see that this node gets replaced with 2328. Instead he crashes, which kind of sucks. Because at 45, we just did a dumb, stupid. keys.len +1. +1. Okay. Boom, 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 boom. 68 comes in here. We're hoping to see that this node gets replaced with 23, 28. That's really big. So that's working correctly. Now we just have to like juggle the stuff to put them in the right spots, right? So we need to, I guess this is going to be, there's two, how many new things do we need to make here? I think we need 3. We need 3 new nodes to split the root. We need the new root node. We need the new root child and the new root child's child, right? Because like we said before, keep in mind that like each of these nodes have like valid child IDs, right? So this is pointing to like an empty guy. This is pointing to an empty guy. This is pointing to an empty guy, empty, empty. So when we split this thing, 1, we need a new node to put these 2 things into. 1, we need a new node to put like, he's going to have like a third guy. So we need a new node for this, and then a new node for the root. Okay. So we'll say new child ID, new grandchild ID, and new root ID. This guy gets the grandchild ID here. To me, this looks like an overkill sorting system. So the idea here is that you want to have a tree of sorted elements, and you want to be able to insert and remove elements from that sorted tree. And you want to be able to like iterate them fast. So B-tree has all of those properties. Hopefully, that's kind of what I'm not like super sure here, but B-trees are supposed to balance that because you have a lot of elements per node, which is good for like cache coherency, right? It means that like when I load 64 bytes from memory into my cache, I'm likely going to use all of those instead of using like a small amount, and I can just rip that section of the node of the list. And then you still get like some of the nice properties of a tree structure that say easy insertion and removal, but they're at like a grouping level, if that makes sense. So it's not overkill. It's like a thing that exists for a reason. But you're right. If you just wanted to sort elements, this is not how you would do it. Or it's how some people might do it, but it's not how I would do it. Okay, so new child. New child. This is B-tree get by node ID new child ID. What kind of application would this be used in most commonly? I think just like anything where you want a sorted list of things that will change. So if you're like inserting and removing elements from a thing, and then you're like, now I want them in order. That's like I don't have like an example off the top of my head, but it is a thing that comes up often. Okay, new child. This guy. What does he get? He gets. We want to set the contents of this guy to the right half. Why have you chosen Zig? Is it cool? I like it. Is about the extent of it. It feels to me like a nice balance of like new stuff that I liked in Rust, but with like less limitations and simplicity that I like from C. That's about the extent of it. I think there's a lot of similar languages. I haven't tried like Jai or Odin. People keep telling me they're similar. But it is what it is. Okay, so now the root now gets like the center element. And he has 2 children. The children that the old node and the new child. So our root goes, I guess we need the root. Get by node ID, new root ID, boom. And we say set contents here. And the keys are literally just like the splitter center element, center key. And his children are the existing node and the new child ID. That seems pretty good. Okay, so now when we build this thing, we're hoping that when we get to this step, we literally just see 68. Okay, instead he crashed, but we were hoping to see 68. So what happened there? How is this not right? Keys plus 1, 1, 2. Am I high? Oh, this is on new child set contents. So that means that this guy is probably plus 1 here. Good thing I had that assertion. Okay, we're hoping to just see the 68. We're not. Because we didn't update the root node. We need to update the root node as well. So we need to say the B tree root node is now new root ID. Boom, 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 boom. 68. Okay, cool. Now all we're missing is that we need to, I think it's just in the visualizer, we have to show this now. So let's look at the data that came in over the network here. And he's got all of the content here. It's just the tree is not right now. Okay, so we need to update our, we need to walk the tree and like build it into JSON so that we can show it in the visualizer. So I guess that this was like more like initial fill, root, and split. Okay. And now we want to do a little depth first search. Or depth first walk. I guess. Boom. Okay. Chillin', chillin', chillin'. So before we were doing this with implicit node IDs, right? As we've said a few times, we used to just store root, his children, their children, right? Blah, 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 blah. Which means that like iteration of these things to do a depth first search was like pretty straightforward. You just kind of like calculate where you need to go next in this array. This is no longer the case for us. So what is the case for us? We want some sort of like depth first walk. I think that this needs to be a function because maybe it doesn't actually now. I guess he needs to be a structure, and that structure is probably gonna live in here somewhere. It's fine. We'll just slap him here. Fuck it. Okay. So in order to like walk up towards his parent, he needs to like keep a stack of how we got there, I guess. I'm curious if we're going to have to store parent relationships later. We might have to write down who our parent is in order to like walk up the tree. But I'm not 100% sure about that, so I'm not going to like force it right now. So if we're going to do a depth first walk in like this world, this is going to return some sort of like output. And here he is going to stash like his level, how far deep he is in the tree, as well as like the node ID. And I think last time we were working with this, we said it would be nice if he stored if he was like entering or leaving. But we'll see if that's like easy to implement. Okay, so this guy's going to surely need a B tree. He's surely going to need to store one of these somewhere. And he's going to, I guess, have some sort of like stack. Where have I walked so far? I've gone somewhere. Where am I? Which means that this is probably like an array list, probably. And here he's going to have like, we'll call it a stack item because I don't have a better name for it right now. So stack item here is kind of like, if we were to write a recursive version of this thing, this holds all of the arguments for this iteration. Right? So as we walk down, we go, we're walking down some tree. And I guess we have like we start here at some node ID, and then we go here to some node ID, and then we go here to some node ID, right? Boom. Now, this guy has no children. Okay, so then we have to go to his sibling, right? So we have to go back up and back down. Boom. Which means that here we must have to store the node ID, and we must also have to store like how many of his children we've iterated. Right, so we need to know how far we've made it across this. Simple. Simple, simple, simple. Okay, which means, how does this look for us? On initialization, we must have to take in some allocator to construct our stack. And the B tree as well. So I guess it's just like our stack is a std array list of stack item initialized with allocator. Dude, in Zig 14, you can just write this. I'm so fucking amped for that. That's gonna be sick, dude. That's gonna be sick. But for now, I have to do this. Child index is 0. We are at the first child of the root. Okay. I guess. Okay. Depth first. I think we want to call this node walk. That makes it a little clearer. And the B. Oh, oops. No, sorry. B tree here. I'm a dumbass. I guess we do want to inject the first element here, though, probably, huh? Yeah, I think we do. Okay, so here I guess that means that we say like stack is equal to this. And we immediately try to put something here. And it's like node is B tree root probably. We start at the root and child index is 0. All right. Where did you learn all this? By doing things? Yeah. Yeah. By doing things. Error differ, stack dnit probably, not that it matters. And okay, so now we just have to like do the walking. So I think that we want to, let's think about like how we're going to use these things. I mean, some specific books or podcasts in mind to recommend. I just do. What you are witnessing right now is exactly how we learn stuff, right? We look at there's like a B tree Wikipedia article, right? We're like, I want to make a B tree. And what we did not do is I did not look very carefully at this intentionally, right? So there's like an insertion list of steps. Close your eyes, blah, 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 right? No looking, cheating. Instead, what we do is we're trying to figure out, like, based off of basically this picture, right? How do we get the right answer? So we read a little bit because there's a thing we want to accomplish, but we don't read the details. Instead, we try to figure the details out ourselves. And if you do that enough times, you figure shit out, and then you get how stuff works, and you have like a bunch of tools in your belt and like an understanding of like how you could represent things. And then later, you like stack that with doing this a million times in a row, and you know how to make stuff, right? So other people learn very differently, right? I'm not claiming that people should do what I do, but for me, what works well is like guess and check, baby. Guess and check. Okay, so let's think about a little bit how we're going to use this thing, right? The reason that we're writing this node walker is because we want to build a JSON tree of this stuff to pass to our visualizer. So the tree looks something like, I think it's like node here and then children, right? And then in the children, We have node. Maybe this is easier now. You know what? We don't have to do this. I'm only now realizing that the reason that we did this before is because we didn't have the tree structure. But the tree structure exists in the storage now. So all we have to say for the visualizer to work correctly is we just need to give it the root ID. Fuck this shit. Just, yeah, fuck this depth first walker. I'm pretty sure we don't need it anymore. We can do the... I think, yeah. I think that here instead we just say like root node. I suspect that this is all we have to do. I'm kind of curious to try that. Okay, so here, surely now this won't work because the data storage format, the data's wrong. And then also, I think that we probably, as we iterate the data section of things, we must have to store like keys. We must have to store like keys and children. So like keys is this stuff, and then children comes down here. Yeah. So node num children. Okay. So if we were to do this, and then hits, oh, this breaks, because I fucked up the object beginning and end. Where? Okay, so we have begin object field, we write an array, we write an object field, we want to write an array of children. Okay, refresh. Okay, so step. We don't really expect this to work, but what I'm hoping to see is that data now will have some valid stuff. He does not, because probably step doesn't get defined here, which kind of sucks. So I would love to check if the data is right though. So maybe we pre-jack this guy with a few values. So let's go 4, 0 to test start. Can we do like btree insert insert sequence at I? Okay, so then we just need an insert function, which doesn't exist yet, but that's okay. We can make one. The insert function should just be like make our inserter and then while val inserter step, we keep going. So it should, now we should be able to pre-jack this with 4 nodes and look at the data. He's pissed because this guy needs to return void probably. He's pissed because this guy needs to, whoever calls this needs to write try, I guess. All right. Okay, so now we refresh data, and now we have like valid data. Okay, chill. So we can see right here that we have a bunch of empty nodes, as well as root node 0, we can make this bigger. Root node 0 goes here. We have these keys and these children. Hell yeah. Okay, cool. So we don't actually have to build the tree anymore. It's kind of implicit in the data. So it just means that our index, our visualizer, he's just got to iterate the data correctly. So when we do node layout tree node here, we walk over some data. Okay, so who calls this? This data, we don't need tree. But we need some sort of like initial value, which must be root node. It has to be. Okay. So then when we lay out the node tree, we have this element here. Good. And we're looking at nodes push elem.node, which is wrong, I think. I actually don't know. What is this supposed to be? The node ID? So I think this is just elem. Then we go for data of data elem keys. We push that stuff. And then to look at his children, we say for child of elem data elem children. Cool. And now we have a problem here where we need to fix the fact that these are supposed to be node IDs, not like the strong type versions. So that's fixable for sure. We just need to make sure that when we somewhere we have like begin array in here. When we serialize these things, we just have to write value here. All right, let's try it again. Run that bad boy, refresh this. Okay, so now I have children 1, 2, 3, 4, 5. Hell yeah. If we go back to the visualizer, did that fix everything? It did. Look at that, baby. So we've got our thing. We've got some empty children. We step. Oh, come the fuck on, man. Wow. That's hype. So yeah, you can see here. It would be nice to get some more intermediate state in here. But that's pretty sick. Pretty fucking sick. Okay, so like, how do we visualize the walk up now? Because before it was very clear that like, before it was like 76, 92, 23, 28. They go their own ways. And then we take the 68 and we move him up. And then we inserted the 68 later. And I'm concerned that that doesn't work anymore, right? The whole new pattern that we were working towards is that we don't insert until we know where it's going, right? So at the root, that works great. I think that we just have to start adding more stuff in here. And I think we can start seeing how it like falls over. I'll rename this from depth first walk to serialize like fix visualizer. And now we can start working on like whatever the next stage is, which I don't know what it is. It's like, I guess it's like second layer node split. Okay. So first of all, we need to make sure that the root node gets flagged correctly as a parent. So he needs the node type here to be an inner node because he's no longer a leaf node. And that allows the like search of where we're supposed to go to continue on. Except we're not actually searching right now. That's a piece that we're missing. So after the split, we shouldn't just insert into the root node. We need to insert into like the appropriate node. So what we have to do is we have to walk down this tree. We have to walk down the tree. Boom, boom. We get this 34, right? And he's supposed to go 34, that's less than 68. I'll come down here. So he's supposed to find this. So he's the old version of this function. Use this like tree walker thing. I don't really know if we need that. But we had some sort of function that was like find elem. Find key, I guess, is the word. And he's going to return some find result. And last time we found that flagging if this thing existed or not was very useful. So we had like exists bool, great, and then we had the node ID. Where did we find him? And so here I guess we start at the root. So we say like, I guess it's like var node is get by node ID root node. Okay. While node type is, I guess it's just while true, maybe? I guess it's maybe while this is not equal to leaf. Maybe? We'll see. While we're not at a leaf node, we check if we're above, below, or equal to the thing. So I think that we iterate over all of the keys in this thing. Yes. Yes. Like this. Then we do like, we check if we're greater than, less than, or equal to the key. If we are less, then we're like chilling. We need to like jump down the layer, right? So if we're like 34 and we're less than 68, we have to go down here. So if we're less than, we probably break. If we're greater than, we continue, right? So if there was like a 12 in here, then we would go 34 greater than 12, 68 less than 68, right? And if it's equal, we have to be like, we found it. So here we need the node ID. Which I guess we just say like, we probably do something like this. Then presumably this node ID will get updated. Presumably. So if we find it, we probably like assign node ID is equal to the node ID that we're, the key. It's actually probably, I think we want to do for 0 to num, for 0 to node num keys. I'm not sure if this triggers like a recalculation or a read function call or anything, so we can kind of do it like this. Key is node keys at I. Then here, I guess if we are less than this thing, so we are less than 68, that means that we go to that child, the child at I. So this is keys I, we go to child 0. So we say node ID is equal to node children 0 at I. Then I guess probably node gets actually calculated here. This is probably while true. Then we need to make, then down here, after, at some point we need to like break out of this thing, right? So if node, yeah. Yeah, so what is this? We say if the child is, if we're a leaf, if the node type is a leaf, then we break. And probably we want to return like node is equal to node ID and exists equal to false. And then this is a little tricky because then this means this is wrong. Interesting. because like we don't want this in this case. Um. I guess it's literally just this. I guess. No. Yeah, maybe like this. That might be right. It might be. So then we have to like call find key here. Right? We find key val. And if res exists, I think we said last time that it's nice to return an inserter that is just already finished because that helps with the visualizer. So we just still do all this stuff. We say val is val, target is res target, btree is self, but the state is equal to finished. Otherwise, we'll return the same shit. All right. Let's see how that works. Find key is pissed because I didn't write self. It's fair. He's also pissed because target is wrong. It's node, not res target. Okay. Get by node ID is pissed because at 240. Can we just for now write like const? It's fine. It's fine. Okay. Step, step, step. Okay, so now he's correctly identified where he's supposed to go. Hell yeah, dude. And then he's kind of inserting his child. Technically, I guess, he doesn't need to insert the children until the thing is no longer a leaf node. But I'm not going to fix that right now. But I should fix it eventually. So I'm gonna put a fix me there somewhere. I guess on like split or set contents maybe. Here we should say fix me only needs children if inner node. So we eventually do need to fix that, but for now we will not. And we will just kind of hack it in the visualizer. So if we go into the visualizer and we just say like, when we lay out a tree node, we just go like if data elem like keys len equals 0, we just return. I think that kind of fixes the bullshit, like the ugly visualization. Not quite. Why did that change anything? Why doesn't that work? If data elem keys length equals 0, don't do anything? That seems like totally fucking sane. Oh, we need to update the y though, still. We need to return y, I guess, for this to work out. There we go. There we go. Okay. So now we're in this state. This is probably broken as fuck. So what just happened there? We put in here. So can we like snapshot this state really quick? And can I just like view it? Okay. So we had the 23, 27 That makes sense. That's here. 34, 35 gets split. Oh, it's because we're treating this as a root split when it's not. Okay. So now we need to implement normal node split, which is different than the root split. Okay. So split node. So this guy, what's he gonna do? We should, okay, I would love to leave this server running actually. I would love that. Just so we can play around with it. Okay, so what do we expect to happen here? These guys shift to the right. This guy comes in here. Boom. Too much shit. Too much shit, man. 28 comes out. 34, 35. Get a new node. Yeah, so it's... So 34, like, right half gets new node. Okay. Chill. Then, what? 28. And the new node is not yet inserted. We don't know where it goes yet. That was kind of the whole point of this change. Instead, they get carried up with the 28 up the tree. So right half gets new node. Middle element returned to injected into parent. And when injected, we insert like tree segment into correct spot. This is the sequence. So, yes, that means that this guy essentially needs to hold like a in progress tree, not this guy, or like node splitter. No, not this guy. The inserter. Yes. This guy needs like in progress tree. And this is just going to be a node ID, I think. Right? So I think what happens here is on the first split, we like create this guy. Then if we had to go farther up the tree, this 28 goes here, he overflows some stuff, and he like brings some more guys with him. Yeah. Something like that. It's something like that. I'm sure that it will expose ourselves as we go up, but for now, we say 28 comes out. 34 and 35 comes with him. So we need a new node. Is this. We append an empty node to the node tree. We're chilling. And for now, what? We use the same node splitter. Who also needs a new grandchild ID, I guess. But this is again, fix me, like leaf nodes don't need children. But for now, we've kind of like written it that way, so we're just gonna keep going with that behavior. So we get the current node, we say new grandchild, boom, we have our node splitter. Okay, so now it's like simple. We like our existing node. We set the contents to the node splitter, left children or left keys, and left children. Okay, simple. The new node, this is a new node ID, I guess. I guess we also need like error differs. We need like some way to clean this stuff up if it fails, but I don't really know what I want to do there yet. It's probably just an error differ pop. Probably, but I don't, whatever. We'll figure it out later. Okay, so the new node This is the get by node ID, new node ID. Boom, simple. And he gets the right half. Right keys, right children. Oops, new node here. Okay, so now what? We said this stuff was here, 34, 35, boom, new node gets the right contents, right? So we've got some nodes in here. Now I guess if self has an in progress tree, like that has to somehow get like attached as a child to this shit, which I'm not quite sure how. I'm not sure how. So instead, I'll just say that the in progress tree is equal to the new node ID, because I don't really understand it yet. So this 34 and 35 will just kind of sit here. And then we say, I think that we want like next target or like next step. And we're going to be like, okay, we're now going to have like a new target node that we're looking at. And we're going to have a new value that we're inserting. So the new value is going to be, target is, I think this is back, yeah, no, target is the parent, which I don't know how to get right now. Yeah, that's kind of funny. We need some way of going to our parent easily, which surely we have. When we found this thing, we know where we came from to get down here. So I suspect that we're gonna have some sort of like parent stack here. Right? Something like this. And we can like walk our way back up by just like moving up the parent stack. That's kind of my idea right now. Right? So it's like this. And we're like, okay. We look at the target and what's the other thing? Value is the node splitter center elem. Okay. So we're like, now we are inserting this key over here. Please, thank you very much, sir. Okay, so that means that we need to construct this parent stack in find key. This is what makes sense here, which means that here we have like an allocator and we say var parent stack is equal to std array list node ID initialized with an allocator. Boom. Error defer parent stack gunit. This thing can fail because surely do something like this, right? Okay. So now on each layer here, we look at the parent stack last. Okay. And here, I guess it's something like this. Parent stack is parent stack. And if we get to the end, it's still parent stack. Do the parent stack. And now it's just, we push this thing. That feels kind of right. Feels kind of right. So now when we get this guy, it's like, what do we call it? Parent stack in the inserter? Yeah, we did. We have like parent stack is equal to res parent stack. Wow. There is no more target anymore, but I guess it could be like parent stack pop here. Yeah, it kind of feels like it should be like this. Something like this. So we get the last thing in the stack. Yeah. Something like that. We'll see. Okay, so does this build in its current form? No. Because now find key needs an allocator. Which is a little annoying. Yeah, this is like annoying all around, but it's fine. And I guess really we should call this like a temporary alloc here. And this is like an allocator that is related to the inserter. Okay, cool. And then probably here we go like, we just huck the allocator in here. Okay, and then surely like we need to do like val inserter dinit after this. Because this guy has an array list in him now, which seems pretty shit. I'm pretty against this, to be honest, but we're kind of where we are, and we'll figure it out later if we don't like it. Maybe we find that there's a way around this later. So here, can we just say, fix me? Allocating here seems kind of lame, we'll say, but we'll figure it out. Okay, so now I think this becomes split node. I think it's probably like if the parent stack items len is equal to 0, we call split root and we're finished, right? Otherwise, we go split node and we're back in the append state. That's kind of how I'm feeling right now. Cannot assign to constant, 202. True, because I made this const. It shouldn't be anymore. 164, right, so this needs to be like next is this, self target is next val, and self dot val is equal to next val. I guess it's the other way around. All right. B-tree inserter is mad at 589 because we didn't make him with an allocator. And here you probably want to do inserter dinit before. It's actually I dinit here, I guess. There we go. Okay, 602 is pissed off because he needs an allocator here. Okay, and then if res exists is mad. because this needs to be tried, because you can fail, which means that this thing needs an exclamation point, which means that this, everybody who calls this needs to write try here. Boom. All right, we're moving. We're getting somewhere. Try val inserter step is 268 mad because this thing needs to write try here. Parent stack at 322 needs to pay parent stack. Oh my god, it's so hard to type. 279 is mad because I can't fucking pop off the stack. Ugh. If I write var here, I think it's okay actually. Nice. 275 is mad because I need to set in progress tree to null because it doesn't exist yet. Okay, I think that we are chilling. Okay, so now we can kind of see what type of like bullshit we've ended up with. I actually have absolutely no idea what I expect to happen here. So I guess I kind of expect that the 27 will come down here. The 28 pops out. The 34 and 35 will kind of disappear for a little bit. And then the 28 will come up and try to get inserted into the root, which is what happened. It kind of all happened like really fast because I think I forgot to return somewhere to allow inspection. And then what needs to happen is when we split the root, we need to like insert, I guess it's not even split root here. It's if the append succeeds. If an append succeeds, we need to like take the tree that we're carrying up with us and put it somewhere, right? So add to node, self target, self val. I kind of feel like this just belongs here. I don't really know how yet, but you know, we'll kind of figure it out as we go. So I guess what's happening here is it's like in the normal case, add to node. So we just append this thing and sort, which is no good anymore. We can't do it this way. We can kind of do it this way in the root case. Here I'm just going to assert that child is equal to null because I don't know how to deal with this in the root case yet. Or in the case where the thing is fucking empty. I don't think that should ever happen. And here, we actually have to intelligently figure out where to place this thing. Yeah, so we have to be like... for 0, node to not... for however many keys there are in this thing. I guess we kind of do it like this. Key index is 0. We say while key index is less than num keys, we increment this thing. Yeah. And then we have to like walk over all of the keys in this node that we're inserting into and figure out where we belong, right? So I guess it's like if node keys key index is greater than val, this is the place. So now we have like where we're fucking putting this shit, right? And so we should be able to be like, maybe it's like node, like insert at, maybe it's insert at some key index, the val and the child. And I guess we have to say here, like, if child is equal to null. Yeah, it's here. It's here. If const new ID equals if child here, we use the ID. Otherwise, if there is no child, we need a new child. Cool. And so this is the like, you know, like insert child ID here, and that goes here as well. And now we just have to implement this like insert thing. Yeah. Yeah. Okay, so how do we fucking implement an insert? We have key t child is a node ID. And I guess it's like, we also need like a like index. Where are we putting this thing? Okay. Is that how we fucking called this? Yes. Okay. So we must need to move stuff. It's called copy backwards. These things are backwards from the way, or sorry, it's like named backwards from the way I think of it. But basically, copy backwards says desc pointer has to be greater than or equal to source length if there's overlapping. There is overlapping here. We're gonna copy from keys index onwards. We're gonna copy that to keys index +1 onwards. So self num children +1, I guess here, and self num children. And it's actually here, the keys is not the same as num children. Are we taking a break from the Photoshop killer, or is this inside this project? Eventually we are planning on going back to it. But it's been a while since we've been working on it. I want to finish the code map first, then go back to the Photoshop killer. But I do have like, it's like I other times I've said that and been like, oh, I'm not so sure. This time I really do want to go back. I really want to go back. We'll see if we get there, but I don't know. We'll see. Okay. So this is num keys +1 and num keys. Will code map work on any repo? I mean, probably not any repo, but I am intending on having it work on not just Zig and not just my code, but we'll see. Okay, so that seems kind of reasonable. So then we also do the same thing for children, where we kind of move them all forwards from the insert index. Boom, boom. Then we should be able to say that like, I guess this is the key index here. We should be careful about this because the key and the child index are off by 1 from each other. Self children at self key index or key index +1 is equal to child, and self keys at key index is equal to key. Is that correct? Yes. Okay. And then self num children +=1. All right. So that might work. This guy's mad because it needs to be like, we need to append this thing and also say new ID is self storage or self next node ID, and then break block with new ID. Gross, but whatever. Whatever. Expect U8 find usize, so we'll just do this for now. Copy backwards needs us to know what type it is. So this is T and this is node ID. All right, let's see what happens. So this guy, we're hoping he comes in. Okay, first of all, this is not sorted, which is not good. That's not good at all. Not good at all. So these, yeah, even like off rip, this is a problem. Do you normally discover the next project while working on your current thing? Yeah, I think that just like I have like a list of things that I want to do, and the list just always grows. It always grows, and so there's just like always more to do. Okay, so this must be the sort elms change here. So it means that this insertion must not be happening at the rain index. Can we change this back to say test start is the first thing? Okay, boom. So 76, he comes in here, that's right. 92, he goes in the right spot. 23, he looks like he's sorting one to the right of where he's supposed to be. So that's pretty easy to fix. That just means that we do it. The key increment happens after. So 28 comes in here, 76, 92, 23 comes to the right, great. 68 comes in, he splits them up. 34 comes in here. Ah, fuck. 34 comes down here. 35, he should end up right here. Boom. Okay. So now the 27 should split this stuff, right? So we should see kind of something like this. The 28 should pop out here, and the 34 and 35, I think, disappear. Okay? And then what I'm hoping to happen is that the 28 comes in here, and the 34 and 35 reappear here. Mwah! Mwah! It's beautiful. Okay. So now what I would love to do is I would love to visualize I would love to visualize the like in flight side of the tree. But maybe that's a problem for later. Okay. So can we just keep going now until what is happening? I would love to keep going until it breaks again. So what is happening here? I think there's some sort of infinite loop here. Find key. So this while true is happening. This num keys, we're going greater than greater than greater than greater than. It would be nice to see what we're trying to insert here. Maybe we run this again. Okay. So we're trying to insert 75 here, which means that he's getting to here probably, and he is the smallest element. Can we just kind of finish? Okay, so find key is never exiting. And then probably this like stack is getting like huge. Yeah, this parent stack is getting bigger and bigger and bigger and bigger and bigger. So that's a problem. So we need to go here and we need to say if we make it through all of them, I think it's something like we get greater than every time. Then we need to go down a level, which we are doing. Okay, can we let's just breakpoint on this function and like really step through it methodically. B1 condition 1 val equals 72, right? Okay, refresh. Okay, it didn't work. Why? Because it's 75? That would do it. Okay. Still no? Okay, cool. B tree, okay. Frame. Like. The fuck? Maybe I have to breakpoint like here or something. Cause like. condition 1 val equals 75. Or it's one of those like optimized out bullshit. Oh, there we go. Okay, cool. Cool. So let's slowly work through what's happening. So we're looking for where 75 belongs. We have node here, which has keys 28 and 68. That's where we're at right now. We're looking here. And so we go, okay, let's look at the first key, which should be 28. And we should say that val is greater than 28. So we do say that. Okay, we go again. And we go, we're also greater than 68. Cool. Then we get out here. And we say, okay, so we've realized that we're greater than every single thing in here. We have to update here that if we get through all of these things, next node ID has to be node children at node num children minus 1. Yes, we were just never recursing if we were the biggest element. I'm pretty sure is what was happening there. He's pissed off actually, which is kind of surprising. Integer overflow. Oh. Probably here. We have to do it after the leaf check. Why are you doing this? Mostly for fun is probably the best answer. Okay, so 13, 75, 2, 27. Okay, that looks like it's working. 91 comes in here. Oh, wait, no, the 2, this is in like the totally fucking wrong spot. Hold on. These guys got, something fucking happened here. 23, 28, 35, 76. Yeah, this is out of order as well. The fuck? Wait, this is wrong on multiple levels. So this is fine. The 68, he comes in, boom, splits these guys. This is still correct. Wait, this is wrong too. These guys are supposed to be coming in here. Whoa. What the fuck? What the fuck? 34, so he's finding the wrong thing here. Oh. Because I'm fucking stupidly always appending the... Oh, this is so stupid. We're always going to the rightmost node. We should only be doing this. We should start maybe like this. Yeah, so we default to going to the right side. But if we find a better candidate, then we switch to that one. And then this might fail, so we need to do a saturating sub, which is fine. Okay, let's try this again. Step. 76 targets this. 34 targets this. Okay, that's better. 35 targets this. 27, he comes in here, he splits this up. The 28 comes up, 34, 35 disappear for a second, and they should come in here later. Boom. Okay. So far, does this look correct? We have 2, 13, 23, 27, 28, 34, 35, 68, 75, 76, 91, 92. Those are all in order. Hell yes. Now, what happens here? 26, boom. 23, up. 26, 27, disappear. 23, here. 26, 27, back in here. That's what we're hoping to see. Boom, baby! Okay, that's really good. That's really good. Now we just have to handle the second layer, which I think should come almost for free now. Almost. Okay, so 79 comes in here, 86 pops out. 91, 92 go into the nether. These got 91, 92 into the nether. 86 comes up here. He goes, I can't fit now. And here we're going to do something wrong. We're not going to do the right thing at all. But I wonder what we're supposed to do. Here we're probably supposed to discover that 68 pops out. 76, 86 become our new thing, but we need to append all of these guys as children. That's what we have to do. So these guys have to come here. And then when we figure out how to insert the 68 here, is that right? No. 79 comes down here. 86 pops out. 91, 92. Uh-oh, I don't fit. Which means that... Yeah, so 86 comes up here. Then we go, uh-oh, 68 doesn't fit. This is like this. Yeah. Then this makes it up to the root. This comes up to the root, and then he goes, we're splitting the root now, and so this guy gets set as the second child. Okay, that makes sense. That makes sense. So our inserter guy, I guess what I want to do is I definitely want to visualize this like in-flight thing here. This thing, we gotta visualize it, or else we're gonna lose our mind. So can we, in our data, can we represent, can we put that somewhere? We can say like, off tree, to be inserted. That's what we already have to insert, which is like the value. So can we say like to insert data, we'll call it. To insert child, yes. And this is gonna look at like, if we have an inserter, and if inserter.inProgressTree, we write the tree, otherwise we write null. And I'm just gonna put like a fix me ew on like ew double nested duplicate nulls, etc. But for now, I'm just not gonna think about it. I'm not gonna think about it. Okay. So now that should make it so that when we're like in progress here, so like right here, this 27 is gonna kick out the 34, 35. Fuck, it's broken. Wait, why? We write in, oh. Oops. We can't write the same, we can't write twice to a JSON field. That would be crazy. Okay. So 34, 35, we're hoping to see somewhere that 34, 35 is like somewhere in our data. Right? So we're hoping to see that this, oh, to insert child value, fuck. This needs to be t.value. Okay, let's try it again. Oh, fuck, wait. It's here. Here, we're hoping that in our data, we say to insert child 11, and the 11 has the 34, 35 with children 2, 9, and 10. Sick. So we now have this like side tree and we can render it. So all we have to do is actually do that. So I guess we should probably do that in like a second window. Just kind of makes it easier because we can just start like spamming refresh as we make our improvements. Okay. So yeah, let's figure out layout node tree. This guy has to, we probably have to do like a double layout here. right? That's kind of what I'm imagining, is that like when we update the layout, we look at the root node and we say like, if this data to insert child is not equal to null, we lay out this thing as well, but we put them somewhere else, right? So if we just put them like, I don't know, like, 400 pixels off to the right or something, and use this. I guess lots of B tree impulse split full nodes while descending instead of starting from a leaf and pushing the value upwards. Oh. Well, what you gonna do? I don't know how you... Oh, yeah, I guess you could maybe do that. That does kind of make sense. Okay, there's our 34, 35. So that's good. That's good. Can we kind of render him like maybe 800 pixels to the side? There we go. So then we see this kind of guy sitting over here. We step in and he comes in. Boom, boom, boom. Boom. 26. Boom. We see the 26, 27 split out here and the 23 come up here. Boom. 26, 27 back in. That's pretty sick. And so now we can kind of see what our guy is doing right now in the case when we explode. So we get the 86, 91, 92 come over here. Then do we crash? We do. Okay. Because split root is falling over on 111, surprisingly. So that's here. Oh, because we've got lucky here where the extra key is too big. So it's node keys, while key index is less than node keys len and this. There we go. Okay, so now this is gonna fall over in a different way, but okay, can we also like pre-jack this shit? I think it's like test start was like 41 last time. Was that the right spot here? Or was that another layer down? No, okay. Too far, too far, too far. 20? Okay. 27, 79. Okay, so it's 22. So the 86 comes in here. We expect this to come like this, 68 to come up. And then I guess we want like some sort of like tree, bigger tree to form on the right side here. Which is... I don't know if that's what happened. There's a 91, 92 in here that I think is getting lost. Yeah, the 91, 92 is definitely getting lost. So it's just here on the root node stuff. It's really when we split root, we just have to make sure that if the child exists, that we use it. So we say like, if we have this like in progress tree, we use that, else we do this stuff. Boom. Okay. Yeah. And then that's not quite it. That's not quite it, because that gives us like... maybe. We'll see what happens if we do that. I'm pretty sure this is wrong. I'm like 85% sure that this is incorrect. What is he pissed about? Hello? Oh, I just didn't save. Yeah, we're still losing 91, 92 is still just going out the wazoo. So like, where the fuck is it in here anywhere in our data? 91, 92? No. I think what ends up happening is we overwrote it. What we actually have to do Oh, wait. I was almost right. It's the grandchild. The grandchild is the one who gets this. Maybe. We'll see. We're really just kind of guessing and checking here. Okay. Okay, so if I get into the state, that's kind of right. That's kind of right. So we have this 91, 92, and then all of this happens at once, which is a little tricky. The 86 comes here, 68 pops up. We say, we need a new. We're going to create a new node splitter for this thing that has a new, like an extra guy over here, right? So we go, okay, 23, 28, 68. That gets the first three children. 76, 86. Yeah, 76, 86 are like these guys. Boom. Right. Boom. Boom. And then we have this extra data and we go, oh, 86 has the extra guys, 91, 92. Boom. And so when we hit step here, that ends up being correct, which is pretty fucking sick. Pretty sick. Okay, so now what happens in the case where it goes like, where we fill up again? Hold on. That's not good. We're fucking... Whoa. It's something's not getting set to an inner node correctly. I think it's like if self in progress tree, that means our new child is no longer a leaf. I'm pretty sure that that's what happened here. Pretty sure. So we step a few times. We should never be seeing this node get highlighted. That would be bad. Okay, that's a lot better. So now we're making it down here. 80 goes in, 85 goes in, 68 is like, I'm already there. This guy gets pulled out some stuff here. The 36 is going to come here. The 41, 46 is going to come down here. Boom, okay. Chilling. Okay. This, I believe, is the next problematic case. So 42 comes in here. 42 comes out. 4650 gets off to the side. Right? So 4650 off to the side. 42 is now trying to go into here. So what's going to happen here is the 42 is going to come like this. 28 is going to come out. And we're hoping to see something that's like 3642 up here with kind of something like this here below. That's what I'm hoping to see. Oh, wait, that's so good. That's so good. So now we have exactly what I hoped for, I think. Maybe not. We need to go back in time. I'm actually worried that we lost something. Why did I close the browser? What am I fucking doing with my life? Okay. I think that we had a test start of like 40 here for this case. Can we go localhost 8080? Is this where we were? No. 30? $31, $32, $33, $34. This is the problem. It's 34. Okay. Fuck. 33? Okay, here we go. So you have the 36 in. We're hoping 36 comes here, 41, 46. Oh, no, wait. This is fine. Fuck. Reset. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. Plus 9, plus 9, plus 9, plus 9, plus 9. Plus 8? Here we go. This is the one. Okay, so what are we hoping to happen? 42. Boom. 4650 off to the side. With 42 up here targeting this guy. Right? So that was fine. It was here where I was less convinced that we got it right. So 42 comes in here. 28 targets this. Which means that these guys become the new thing here, and we bring all of the children here with them. So let's just double check that this looks right. We should see 34, 35, 36, 39, 41, 42, 46, 50. Yeah, okay, so we screenshot this, keep them here, and we hit step, and we are missing the 46 and 50. So we were close, very close. We lost the 46 and 50. Where did they go? It's got to be in split node. We have like the same thing here where the new grandchild needs to take into account if yeah. It's the same thing. Same thing. Okay, wait, so that looks really good. That looks like what we drew here, but like better, right? 36, 42, 34, 35, 39, 41, 46, 50. Okay, so now the 28 comes in here, and the 35, 42 should end up here. Or the 36, 42. Yeah, nice. Okay, so that's looking pretty correct. Now we probably spam a lot more times to see. I guess we just want to like watch to make sure. Oh, this is bad here. That's bad. This should never be highlighted because it's not a leaf node. Yeah. So we have the same problem here where we have to do if in progress somebody is a parent that didn't used to be. In fact, both of these guys, if we're splitting a node, we kind of have to do, like, I think it's all the same shit here. I think. Yeah, we need to set the node type to inner on both of these. No. Only if they have. How do we determine? I guess any node that we're splitting is an inner node, right? Is that true? No, only the new node. The new node is a parent node? Yeah, the existing node is still a leaf. The new node is a inner node. No. Hold on. I don't know who is supposed to flag this shit. Hold on. We're looking again. We need visual aid. So when we split this node, when you split this node, how do I know? Oh, this guy was already an inner node. This guy was already an inner. Is it that the root always creates the inner nodes? No. It's here. It's here. When this 42 comes in here, right now this is a leaf node. This 28 comes out. We move this 3642 over here to a new node. Yes. Okay. It's something about that. It's like new node ID here. If there is an in progress tree already, new node type is inner. That should fix whatever the fuck we were seeing there. It's hard to know when that case hit, but we'll just kind of spam next and look for a new element being inserted into the wrong spot. I think that looks okay so far. Yeah, this is orange, but this should only be orange in this level if there's something to the side. So I think we just keep spamming, hoping that everything kind of goes into one of those root nodes. Okay, and then we're probably soon going to be at the point where we are in danger of overflow. So we go slower. 93 down there, he's fine. Okay, this looks scary. 75, 75. It's a duplicate, so nothing's gonna happen. I guess that's happening because it's a duplicate. 76, 76, yep. Lots of duplicates. I'm worrying that maybe we limited our thing to be double-digit IDs, which might mean that we just run out of stuff. 83, 83. We might not have enough numbers to fill this. 57. Wait, this is new. This is new. Okay. Okay. Hype. Hype, 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 hype. This is where we run into trouble. Maybe. Have we hit this case already? I'm not sure. 57 comes down here. Boom. He gets sorted like this. Boom. 69, 59, 61 come up. He comes up here. We go, uh-oh, 42 pops out. 51, 57 shows up here with these guys as his children. Okay. So let's quickly just write that down. Step. So 59, 61, that's good. Step. 51, 57. Oh yeah, this is looking right, dude. This is looking right. All of those are correct. Okay, so then the 42 gets injected there, and then these guys propagate over here. I think that's working. I mean, we've definitely gotten way farther than wherever the fuck we were yesterday. Yeah, I'll probably try to stress test this some more, but I think we are finally at the end of the saga. I will say that the visualizer, like, holy fuck, holy absolute fuck, is so useful. Like, it just makes it so much easier to debug, and I'm like very, very, very glad we made it. Like, pretty sick. So I think we can call it there. Let's just, like, one more time. We'll just make sure that this is right. 0, 2, 5, 6, 7, 9, 10, 13, 16, 17, 19, 20, 21, 22, 23. This is all in order. Hell yeah. We come up here, 28. Then we get down to 29, 32, 33, 34, 35, 36. All this is in order. We come up to 42, but we don't call 42 yet. Yes, we do. Because we're going to the right side of 42 down here. We don't look at 51 yet. We look at 46, 47, 50, 51, 51, 54, 55, 56. Yeah, I think this is all in order. I think this is correct. 68 up here, 69, 70, 72, 76, 81. Or sorry, 69, 70, 72, 73, 74, 75, 76. And then, whoa, what's going on here? Oh, yeah. Oh, I think we're going off. I think there's more stuff rendered below here, and the canvas is getting cut off. I bet you that's it. That's pretty funny. If we, like, highlight this, yeah. So if I change my height to, like, 4,000, does that fix it now? No, it just fucks everything up. Okay, well, I think that is a success. I think that's a success. You should compare your result to this with a max degree of 5. What is this? Oh my god, it's so slow. Oh, that's kind of fun. Oh, that's cool, the way that they do that. They allow duplicates, which is kind of interesting. Okay. Anyways, join late. You starting to drag numbers caught me by surprise. Printf debugging on super illegal steroids. Yeah, it's pretty sick, huh? Isn't this hype? All right, cool. Thanks for watching, guys. If you like what you saw, we stream most days around 12:30 Pacific time to 4 o'clock Pacific time. It is 4 o'clock Pacific time now, so you should expect us to see us online between 3.5 hours ago and now. If you're watching live and you want to keep up with our projects, there's a YouTube link in the Twitch description. Our stuff is organized into playlists, right? So if you want to check out what we're working on right now, this is under Mizik because it's very miscellaneous, but we're going to get back onto this building a map of my code, and we're hoping to get back onto image manipulation project after that. So swing back by if you want to catch us live, or watch the YouTube if you want to keep up that way. 12:30 to 2, we usually do kind of like a segment called Happy Hour. Today's Happy Hour was implementing this drag and drop shit. So it was like, a little bit of storage rework and like mostly like rendering rework, I guess. But this was very helpful for us being able to like, navigate this stuff. But Happy Hour is kind of like, we do stuff that's like helpful, useful, but I don't want to like commit to like a YouTube video. So if you want to check out the Happy Hours, you've got to catch them live or join on YouTube or sub on Patreon or sub on Twitch. Any of those work. And the VODs will be in the appropriate spots. Otherwise, peace out. Twitch, let's find someone to raid.